Welcome to our Water Talk seminar for this week. I'm pleased to be able to introduce Dr. John Marwitz, who is a professor and head of our Department of Atmospheric Sciences here at the University of Wyoming. John received a BS and MS in civil engineering from Colorado State University and holds a PhD degree in meteorology from McGill University in Canada. Among his many professional accomplishments, Dr. Marwitz was the principal investigator on a 10-year project called the Sierra Cooperative Pilot Project, which was a portion of the U.S. Bureau of Reclamation's Skywater program. This was a 10-year, approximately $5 million effort to study cloud formation and cloud seeding opportunities in the Sierra Nevada. In addition to that experience, Dr. Marwitz has conducted similar research in Alberta and also in the San Juan Mountains in southern Colorado. His topic today, as you may guess from that introduction, is called Winter Weather Modification in the United States. And this has locally been a subject of some interest and controversy in the past year or so in Wyoming, so we're looking forward to John's presentation. Welcome to Water Talk, John.
Well, the modification can go a whole bunch of different directions. I could easily get into the politics of weather modification, and that's an interesting topic in itself. It's full of interesting people, personalities. I'm one of them, probably. One of the duller ones, but still one of them. Or I can just talk about the science, and that'll be a bit boring too. What I'm going to try to do is give you just a little thumbnail sketch of a large number of weather modification projects that have been conducted in the western United States in the last 20 some odd years. I've been involved in a number of these myself, and show you what these are about and maybe how things have evolved where we stand now. And then come down and talk about Wyoming, southwestern Wyoming, where they think they're being robbed of water, and a little bit of data we have on the Wind River Eden-Farson project, where they think they have increased precipitation. Maybe rob somebody else if you buy the rob Peter to pay Paul hypothesis. I guess if I put that there, it shows up somewhere. Where? On the video. Aha. Do what now? Oh, leave the white pad on there? How's that? Well, the idea of weather modification, cloud seeding, first, the primary assumption is that the clouds don't have enough natural ice in them. And the reason ice is important is, if you recall some of your physics background, the water vapor over ice, the water vapor pressure over ice is less than the water vapor pressure over water. So if you've got a cloud that's got a whole bunch of supercooled drops in it, that is unfrozen drops, and then the vapor pressure will be the saturation vapor pressure over water. You put one ice crystal in there, and the vapor pressure over that ice crystal is much less than over all these droplets. So the water vapor starts to condense onto the ice crystal, and the ice crystal grows large much faster than drops. It starts to sweep out these supercooled drops, accrete them, and rime up, and it becomes a kind of a snowball process rolling downhill fast. So the precipitation process with the ice, when the ice phase is involved, has a time scale of about 15 to 20 minutes from the initiation of the ice until the ice hits the ground, maybe 30 minutes or so. Water drops takes hours, and usually by then the air blows over the mountain and evaporates and nothing happens. Well, so how do you make ice crystals in clouds? A person by the name of Vince Schaefer was fooling around in a dry ice chest in the mid-40s, right after World War II, and noted he was trying to cool his ice chest even more, and he dropped some dry ice in there, and he made ice. All the cloud kept disappearing because it turned to ice on him. Well, Vince was a pretty suave fella. He figured out that, hey, this has weather mod potential. And a colleague of his at General Electric named Bernie Vonnegut worked with him, and Bernie Vonnegut happens to be the brother of Kurt Vonnegut, who writes all those weird novels that I don't understand, but my kids do, so that's okay. Anyhow, they then conducted some, well, Vince went out and seeded a dry ice, super cooled fog out in Schenectady, New York, and dissipated the fog, and the wheels started turning, and it was the end of World War II, and airplanes were around, and they conducted some projects where they went and dribbled this stuff into clouds, and there appeared to be some spectacular results. And people's imagination started to run wild. They even seeded some hurricanes, and hurricanes did phenomenal things following the seeding. Well, hurricanes always do phenomenal things following seeding. And, there's a whole interesting story there. But nevertheless, okay, the first project I want to describe is the so-called Climax Project down near central Colorado, near Leadville, Colorado. This was established and conducted in the early 60s, ran for 10 years. 10 years and was randomized, was funded by the National Science Foundation, was intended to be the answer to weather modification in orographic clouds, wintertime, Colorado Rockies, Rocky Mountains. The first 5 years, after the first 5 years, they'll examine the data. The results looked to be pretty phenomenal. They then conducted what they thought was a confirmatory experiment where they went blind, and the people that did the seeding didn't know what was in the rain gauge, and people were independent, and high-powered statisticians were involved. And the initial results at the end of 10 years was that in a number of cases, particularly what they thought were warm cloud cases, as much as a 40% increase appeared in the data. And, everything was terrific. Then people started pecking at it. A number of scientists looked at it and says, well, I don't think this is quite what it appears to be, and this is not quite what it appears to be. And a lot of this had solid basis. Well, there's a number of reanalysis that then went on for another, in fact, I think it was for about 13 or 14 years later, there was an article or two a year written in the journals about the Climax Project. When this all came at the last writing, shall we say, the best results are something maybe like 25% in a few cases with quite high statistics. Statistical significance are pretty good. But a lot of holes got punched into this project. And one of the downsides of the whole experiment was that there was very little physical studies conducted there. I can say there was no airborne physical studies done, and not too many physical studies done other than that. It was, by and large, you seed here, release. In this case, it was silver iodide, because silver iodide is also nucleates supercooled water. And you look in the rain gauge, precip snow gauges, and you don't understand a whole lot about what goes on between the grid generator and the rain gauge. It's kind of a black box, if you will. It still is for Climax in my own mind. Well, one of the spin-offs of Climax was to conduct another experiment, randomized down in the Colorado River Basin Pilot Project. Ridiculous acronym, but that's what it was. There, rather than using a daily precipitation amount, they used annual runoff. And they randomized it. Turned out 3 years were seeded and 3 years were not seeded. Did the analysis with some very good hydrologists, Moise Saitu at CSU, and the results looked kind of confusing, highly variable. They did a post-mortem analysis of this, look at the precip data that they had on a daily basis, and produced some rather confusing, sometimes positive, sometimes negative results. But certainly after 5 years, they looked at the data, and it didn't look at all like it was confirming Climax. It was producing, well, I'll just say, confusing results. We were then brought in with our aircraft. At that time, it was a Queen Air. And we did some physical studies to try to understand these clouds. We found that one important thing down there is that even though they were seeding half the time and not seeding the other half the time, there was a lot of stability in the lowest levels during particularly the early phases of these storms. And the silver iodide that they released, rather than coming up and over the mountain, would get trapped and sit there and sometimes move to the west rather than up and over the mountains. And so the non-seeded days had a carryover seeding effect. Stuff hung around for a day or two, and then the storms would evolve to unstable situations, and the stuff would get swept over the mountains. We also found that the convective situations appeared to have supercooled water in them, and that the stable clouds didn't have any supercooled water in them. There was a number of reanalysis, post-mortem analysis of this project by a variety of people, all good people, and found what I highly variable and highly disputed results. So if you're an operational cloud seeder out there, you don't hold this project up with much evidence to convince people that you should be allowed and funded to do cloud seeding. Climax is still held up as but it does not have nearly the regard now that it originally had. Another early project was out here near Santa Barbara, California, just northwest of Los Angeles. The Santa Barbara experiment or project was again randomized. It was funded by the National Science Foundation. It was conducted by some quite reputable people. The results, the statistical results from that project just were again, in some cases, suggested 100% increase, and over areas that just didn't make physical sense, but very large areas. So it's again, and it's an early one. The Santa Barbara project was 67 to 76, 10 years. There was very little physical studies done there. They were seeding rain bands, and they would come in and seed individual rain bands, and then they wouldn't seed the next rain band that came across. So that one stood with a lot of strength for quite a few years until this one came along, the SCPP, Skippy project, of which this was the 10-year one that I was involved in, conducted by the Bureau of Reclamation Its intent was to sort of confirm the Santa Barbara thing, as well as to confirm the fact that there was a whole series, and there still is even today, a series of operational cloud seeding going on along the Sierra Nevadas. The power companies have been seeding these clouds out there for pushing 35 years now. And I'll talk about some of these in a minute, but the main thing that we found that relates to the Santa Barbara project that we found up here was that, contrary to their results, that they had found this large apparent increases from rain bands, seeding rain bands. Rain bands don't have any supercooled water in them. You fly through rain bands from the first one we flew to the last one we flew. And we flew through, in that 10 years, a few hundred, I'm thinking. I mean, it's enough to dull your wits because they're all full of ice and there's not much excitement in the things. As a meteorologist, as a cloud physicist, they're pretty dull. There just is no significant supercooled water in these rain bands. And hence, there's no physical basis for this statistical result that they found down there, which turned out to be the same thing they found in hurricanes. They seeded these hurricanes and they didn't seed some hurricanes, and phenomenal differences were apparent in the few cases that they conducted. And finally, after a whole bunch of years and a few $1 million effort and international, because they were working with the Japanese, trying to move the project away from the United States over to Japan. I mean, the politics got to be interesting there. But a graduate student from our department, a master's student, was hired by the NOAA to go babysit these probes on a P3 that measured supercooled water, and he babysitted them like we taught him. And they finally got the P3 up to the -5 level, and voila, no supercooled water in hurricanes. Hurricane clouds are like the rain bands, and there's a good physical reason why they should be. No seedability there, no physical basis for the apparent results were there. Even today, there's been at least 2 long-term projects, Kings River and Kern River or something down in Southern California, that's been done operationally, and they've established this correlation between some control areas and the target area from a historical point of view, pre-seed, no seeded situations way back. And in the last 30 years or so, they've used those target control relationships to predict and observe any differences between what they would expect versus what was observed. And the answer, statistics, is that there's about a 6% increase, which I have to say I don't understand it. It doesn't make physical sense to me based on what I've looked at up here. The statistics are still there. The cost-benefit ratios are such that they're still seeding. I mean, I didn't shut them off. Shut myself off, in a sense. I mean, there's practically no research being done in weather modification in the U.S. right now. And a large part of that reason is that, we've indicated from our airplane physical studies that there isn't much potential there. And then there's some politics involved, and I'll get into that here in a little bit. Another project is the Utah project. The state of Utah has been seeding their clouds, let me see, since started in 1974. They didn't seed for 2 years, 83, 84 year, 84, 85 year. 2 years they stopped seeding because that's the time that the Salt Lake was 12 feet above normal. So, you don't seed clouds when people are dying from floods or other hazardous weather. So they stopped the seeding there. The Utah project is, say, an operational project. It's funded by the state of Utah. They use ground generators. We did some physical studies in there for 1 month, April of 78. We found some silver iodide up in the clouds above the mountain, so some of the material was getting up there. The Uinta area, from our studies, certainly indicated that there was very little potential in the Uinta mountain range. And they didn't seed the Uintas after that. I'm not sure whether it was because of our results or some other results that they had, but I'm certainly in agreement with that. There's no reason to waste your time in the Uinta range. There's been some physical studies being done there in a cooperative effort between the National Oceanic and Atmospheric Administration, NOAA, and some state scientists and some of the operational people there. But from what I've seen in the literature and from talking to them, they've yet to solidly approach and answer the questions, yes or no, is there a physical basis? They're doing sort of interesting science at this point, and they haven't, in my mind, married the questions of the operational problems versus the physical seedability of clouds. That has not really occurred very well there yet, I have to say. They've done a typical target control analysis. They look at the precip and runoff in Utah versus some control stations upstream and historical precedents set, correlations established, typical type of thing. The data suggest something like a 12% increase. That's what they tell their legislatures, and that's what I think they believe, and I can't argue with it. But I do have to say that there's been no conclusive physical studies to support or deny that result. Another interesting one, particularly as it pertains to Wyoming, is the Bear River area. So obviously the Bear River is just upstream of us. The Bear River, they seeded that area from 1954 to 1970, and then there was an 8-year hiatus, and then they've did it again from 79 through 83, another 4 years. Did this typical type of target control, historical correlation, plus 12%. No physical studies. Another interesting one was the Bridger Range project. That one was conducted by the Bureau of Reclamation, or funded by the Bureau of Reclamation, conducted by Montana State University. The initial results from that one were some pluses and some minuses, but not very clear. There seemed to be maybe something there, but it was, the outcome wasn't obvious. That one was run for 3 years. About 6 or 8 years ago, they did a reanalysis based on some sort of new physical insight as to what might be happening there. And this one, contrary to most other ones, the reanalysis suggested from a target control concept or type analysis that there was something like 15 to 20% increases under certain cases. This statistical result was sufficiently strong and impressive and respected that they were then able to get some monies from the National Science Foundation to go in and do some physical studies. In this case, they did the physical studies with the in-car king air, not the Wyoming king air. And the scientist on board was Al Cooper, who used to be in our department. They went in and confirmed with the physical studies that what they thought was happening was indeed happening, that there was a good, solid physical basis for these effects. So, what we would need to do now is, if you're going, you go back in there and do a good, solid, confirmatory experiment. If you're going to establish the result at a high level of credence, statistical confidence. Well, let me divert a little bit over here on this Bear River area. This is the drainage for the Bear River. It has its origin down in the Uintas in Utah, drains along the border, Wyoming and Utah, through the Bear River, up to the north and out into the Great Salt Lake. And in fact, this is the drainage area for the Great Salt Lake. What you have here is a trace for the last almost 40 years now of percent of normal runoff that has occurred from the Bear River into the Great Salt Lake. So you see starting in 1979-80, there's been this huge anomalous positive amount of precipitation that occurred. And it was this runoff here, if you look on even a larger time scale, 1840 through 1990, this is the height of the Great Salt Lake. So in about 83 or so, the Great Salt Lake was at the all-time record high in the level of the lake. There had been this previous one back in 1870. And it was this extremely high value of the lake is the reason why the state of Utah stopped seeding for a bunch of years, for those 2 years. But, peaks come and peaks go. The last 3 years have been 10 to 30% below normal in that area in the amount of precipitation and runoff. And they've drained the lake, and the lake, most recent reading is that it's about 12 feet below what the peak value is. They drained a bunch out into the desert, pumped a bunch out in the desert, I should say, as well as the runoff has been substantially less. So starting a year and a half ago, the state of Utah started to seed this Wasatch Range up in here. And that corresponds to this, 10 to 30% less precipitation. And as politics would have it, the people over here in southeastern Wyoming are saying, hey, we got a lot less precip runoff than we've normally had. We think those people are stealing our water. Fairly natural and normal thing to expect. But what you start talking about this then as a downwind effect. What's in the literature? What's the history of downwind effects? Well, you come back to this figure, and this was in almost 20 years ago. Downwind effects were a big deal, a lot of concern. One of the initial analysis from Climax that never got into the literature, but the initial analysis of Climax was that there was indications of 100% increases or so out in eastern Colorado from a statistical analysis. And, you know, that made downwind effects big news. More careful analysis of those data revealed that there wasn't any real basis. There was some sort of a flaw in the analysis, and then I've forgotten what the flaw was. But it never got in the literature, so I can't go even read about it anymore. But I do know that it was these results from Climax. I mean, the first Weather Mod conference in Albany, New York, 1978, when we recruited Dr. Gaber Valley to our department, was a section just devoted to downwind effects, and the Climax was one of them. Some of them was in Australia. A lot of the results from the Santa Barbara project were referred to as downwind effects because the apparent area of effect was much larger than what you would normally expect. Number of projects have been had to have a downwind study associated with them, politically expedient, even though in the target area there was always a lot of difficulty in finding direct effects. It always sort of bugged me that we had to devote much effort to looking for downwind effects when we couldn't find direct effects. But the politics come into play because, you know, people who dance in the clouds are perceived to be miraculous. I mean, much more than they are, that's for sure. Well, as of today, you cannot find any convincing evidence in the literature of a positive or negative downwind effect. It just simply doesn't exist. And I think to me, there's a fairly good reason why. And that is, you know, if you're trying to see Climax, some days the winds blow from this direction and the generators are here, and so you target for this point. And the downwind effects, if there are over here. The next day, winds may be from this direction, so you target for this area, and the downwind effects are going to be there. So all of the downwind effects are going to get fanned out and diluted. So if you have trouble finding effects in the target area, problems are an order of magnitude more difficult finding them downwind. They may be there. I'm not saying that they're not there. They may, in fact, be there. But the effect has to be small and is, so far, submerged in the noise. You can't bring it out of the noise with statistics. Physically, you know, if you're going to argue physically, what's the possibilities? You can argue that, you know, you're robbing Paul to pay Peter, that if you make a positive effect here, there ought to be a negative effect downstream. But the amount of water and water vapor that you remove through cloud seeding, when you add a little dilution mixing, it's really very, very small amount that you remove from what was originally there, and the dilution effect. I can just as easily construct an argument that if you seed a cloud upwind of the mountain, you make a whole bunch of ice crystals. There's going to be a number of cases that rather than these ice crystals growing and falling onto the mountain, that some of them will grow not quite fast enough, and they'll fall just over the edge of the mountain and produce a positive downwind effect rather than a negative downwind effect. The physical argument, you see, is just as plausible. The ice crystals can fall down here, and if they fall into some super cool clouds, you know, they could mushroom and become a phenomenal downwind effect. I mean, that's a plausible physical hypothesis. I don't particularly think it's realistic, but it's possible. See? And that's again the problem that you get into when you're looking for downwind effects. lastly, let me show you some preliminary numbers and data that we've got from the Big Sandy, the Eden-Farson project. This is the annual runoff from the Green River in acre feet versus the annual runoff from the Big Sandy, their target. And there's some X's here, which are the no-seeded cases, and there's about 30 or 40 years of data, annual runoff here, where we've established this correlation for the no-seed line. And in the Eden-Farson area, there was, I think, about 18 or 19 years that were seeded, which are indicated with the solid dots here. And then there's some correlation lines here. One way to do the correlation is just to plot a new relationship between Green River and Big Sandy. And this least squares fit here is for the dots, the seeded cases. Or you can fix the slope of the line, which is the dashed line here, and say, well, I'm just going to say the slope is constant, and I'll do a least squares fit through the data that way, which is the dashed line. Well, let's just, what can you conclude from a plot and figure like this? And this is very typical. This is the kind of results that Bear Lake uses to claim 12% increases, that state of Utah uses to claim 12% increases, that the California operational people use to claim, I believe, 6% increases down there. Well, you just go inspect them, and you see there's about 6 of these dots that fall right along the old historical regression line. So you say, had no effect there. If you count, there's 3 that were slightly below the line, 2 of them slightly below the line, and a third one that was much below the line, suggesting that if, possibilities that you decrease the runoff in these 3 years. But if you're going to look at possible decreases, then you look, well, wait a minute, there's 8 dots, years that are well above the line. Well, we got more above the line than below the line. The mean is shifted. That's a positive result. You can jump on another one here. You can say, well, this new regression line, this new regression line is what I believe, and that one says that when there's a lot of pre-runoff, heavy years, I don't have any effect from seeding. But down here, in these low runoff years, I'm getting about 1,000 acre feet extra from seeding. What's an acre foot of water worth, Steve? $100?
Ask Ari. Pardon me?
What's an acre foot of water worth?
Oh, anywhere from $7 to $1,000, depending on who's going to buy it.
Well, in this
$200.
$200 is a reasonable number, and 200 times 1,000, that's $200,000. If I buy that, if you buy into that argument, the project costs $20,000. That's a 5-to-1 payback in critical water years. Well, there's other possibilities here. I mean, I'm being optimistic with you, but I've got to point out the other possibilities. Maybe what happened is that there was a lot of logging, clear cutting in the Green River. And what logging and clear cutting, does that increase runoff or decrease runoff? I think it increases, doesn't it? Well, if I know there's a lot of logging in this area, and there's none in the Big Sandy. I mean, that's a wilderness area, because I know there's been no changes from like that in the Big Sandy. And I think if clear cutting changes it here, it's going to increase it, which I'm going the other direction here, if you think about it. So I mean, that's if there's a lot of clear cutting in the Green River, so that my historical baseline has changed on me, then there's actually more effect than what appears here. Well, you know, maybe but you know, you got to. Another possibility is that this is just random noise, a statistical error, just garbage, and that's a distinct possibility. So there's really three possibilities. There's that this is just statistical garbage, random fluctuations, and we got cheated, and you know, we got appeared to be a difference when there isn't any. That the baseline changed, or that in fact there is a positive seeding effect. And maybe in some cases that, you know, if it's this one, in other words, major increases in light years, that's not only 5-to-1 payback, but it's 5-to-1 in critical years, and this is a 25% increase, by the way. You know, you're going from 30 to 3 to 4,000 acre feet. So now, what do you do? How do you treat this? I think you treat these kind of numbers depending on your own perspective. If you're a scientist, ivory tower, you demand confidence on your statistics, your p-values of 1% or 5% or whatever, and you require confirmatory experiments, or otherwise it's just interesting data. And there's the right and proper place for that in this world. Then that's what it is. It's just a statistical plot. If you're the banker who funds these farmers out there, and you look at that and you say, by golly, you know, if I'm trying as an investment person, I'm trying to decide whether I'm going to invest in this person or this person, and if I plot similar characteristics and parameters to characterize those two individuals, rarely will the differences be much different than small out of the noise. And I'll put my money where the odds are the best, particularly if there's a potential of 5 to 10 payback. So if I was these fellows as bankers, I'd be jumping up and down. I was the farmer, I was the rancher out there. I'd say this is worth, you know, I'm willing to invest this kind of money if there's a 20% chance of a payback, but the chance of payback is 10-to-1. I'll invest, and that's a good investment by anybody's stretch of the imagination. And that really is the problem with the weather modification, is that the paybacks are so large, the potential paybacks are so large compared to the investment, that if you approach them from an investment point of view, kind of like insurance, throw a little money at that with potentials, possibilities, and people produce numbers like this, that okay, once in a while I may lose money from it, but okay, this isn't a bad, these are heavy years, I'm just tickled to have less precip here anyhow. By the way, and then you come in and what do you do to enhance these kinds of numbers? Well, you try to do physical studies. You look at things more carefully. And one of the things that we've noted is that this lowest year on record was followed by this year. So maybe what happened, maybe, is that it was so much, the soil was so dry that even though they increased the precip, a lot of it had to recharge the aquifer. And it didn't happen over in the Green River as much or something. I don't know. You know, you can conjure up possibilities. So maybe there's a physical reason why, if this follows this, that you should have it. I don't know. But that's the kind of you know, an in-depth look at the things. And there's a lot of other data over in the Big Sandy to do some more in-depth examinations to see, you know, is there plausible reasons other than cloud seeding why this point is this far above the line, or this point, or this point, or this year is this far below the line. Maybe there is, maybe there isn't, but you know, it needs to be looked at. Well, okay, I think you should have gotten the tenor of it. The whole philosophy of weather modification, politics of the thing, makes for interesting debate, particularly at the bar. But I guess the bottom line is, if there's a drought, it's time to seed clouds. If nobody's seeding, if somebody's seeding, it's time to hang the cloud seeder. And the converse applies. If it's flooding and somebody is seeding the clouds, it's time to hang them. If there's nobody seeding them, then don't know if you can come up with a very good reason to decrease precipitation, but possibly. I'm tickled to answer any questions you might have. Jim.
Thank you, John. Let me just comment on the economics before we have questions. You know, and there are a couple of economists in the room who can do this better than I, but agricultural water is probably more in the neighborhood of $10 to $20 an acre foot. Something like a municipal water supply might be in the $200 range. But other questions for John?
And if it's $20, then it's a one-to-one payback. Yes, ma'am.
I have a question about the actual process. How much silver iodide is put into the clouds, and is there ever a concern about it getting into water supply? I don't know, is it toxic, or is there anything bad about it?
There's all kinds of, I mean, when you do the rain dance, yes, that you look at that, and it's been looked at in lots of detail. But first of all, a gram of silver iodide is about this much. From 1 gram of silver iodide, you burn it in acetone, vaporize it, and it condenses back as a crystal of silver iodide, very small. From 1 gram, you get like 10 to the 14, 10 to the 15 ice crystals. And probably in the Big Sandy all day long, on the order of 100 grams I would guess that they seeded with. I'm not sure what that number is, but on the order of 100 or 200 grams. The dilution, you have to go to, even to find it in precip, and people have looked hard. I mean, that'd be terrific, just to do the experiment and find it in precipitation, so to confirm some of the linkages there. You got to go with electron, let me think, what's the right word? Help me out. It's parts per 10 to the 12th. So what electron, I can't think of what widget you use to measure it with, but you got to be pretty exotic when you start measuring 1 part in 10 to the 12th.
What other variables did you consider in your equations? Obviously, just comparing stream flow to stream flow is a fairly simple comparison.
Mm-hmm.
When you did the further analysis, you probably compared temperature and what other types of conditions did you?
We have done no more than this with Big Sandy, with the Eden-Farson project. And what else there is to do there, can be done rather, is we as a department were instrumental and conducted this project for the first couple of years for them, funded by the state. We had a device and procedure worked up where we would release a balloon and measure the winds in the first 4,000 feet above the ground. So we have the wind speed and direction in the first 4,000 feet. We have the temperature and dew point. From this we can estimate what cloud-based temperatures should be. And the winds were used to target, you know, where they placed, did they have their generator located upwind of where they wanted the big Sandy? We don't know that. You know, those data are just written on pieces of paper and are in boxes somewhere, so have never been looked at. Beyond that, there's not a whole lot you can do in that area. There are the Raywinson data, sounding data taken at Lander every 12 hours by the National Weather Service, give you some idea about stability, vertical profiles of the winds, temperatures, things like that. But that's about the limit of what you can do in Eden-Farson. You know, if you have an instrumented aircraft, then you go in and you can do a lot of other things, or Doppler radar and various, you measure the winds, things like that.
It's just that it seems like there are so many other factors that could have an influence on it.
Yes, that's right. So this is a typical example of how an operational seeding is done. In fact, most operational experiments don't even have that good wind and temperature data that we collected there. They just seed and then they look in the rain gauge. Keep the cost down and do a statistical analysis. You start bringing airplanes in, it starts costing a lot of money. But yes, there's a lot of variables, there's a lot of noise here. And then again, it is very difficult. It takes a lot of effort to reduce the noise to get the correlation this high. And that's not a bad correlation. I think that's like 0.8 or something like that. Correlation coefficients. It's pretty good. And particularly if it has to do with meteorology.
I'm not sure if you mentioned it or if I understood what you said. What are the downwind effects? Have somebody shown that if your seeding was successful in this area, it actually took moisture away from the downwind area?
No, I thought that's what I tried to say. It's just sufficiently important here. I'll just restate it, and that is that to this date, there is no literature that is accepted or respected or that you know has much strength to suggest and support downwind effects. And physically, I think you can explain that because the downwind effects should be highly diluted. So if you can't find any confident, I mean, we sit and argue about this figure. Now, if I'd show you similar figures for 100 miles downwind of Eden-Farson and tried to convince you that there was something there, I think you would have left an hour ago. You wouldn't have been convinced at all. And that's the problem you're facing.
Okay, if there are no further questions, thank you, John, for an interesting talk.